Thank you very much. Well, my last talk is of this day, so you're definitely tired. So I'm not going to. At least I'm not going to write many formulas, and my aim is mainly to present some observation, which seems to me amazing, and it kind of brings together different subjects, which are each of one well known, but for me it was, well, kind of surprised that they fit together. And the main object which I am going to introduce is some kind of colored graphs, which play a role in, well, in many aspects of mainly cluster things, but, well, or rather in higher-type mirror theory. So this is in this domain. So I, since today there were plenty of talks, plenty of well, introduction of cluster varieties, so I'm not going to spend much time about that, but I'll just kind of how you usually fix in notation. So what I'll say that, well, what is cluster duality, by the way? Cluster duality is just, well, we have a cluster variety, which is, as before, it is denoted by A, and this is actually the union of is glued of coordinate charts, which are just C star to the power of n, so it's some smooth variety. And well, there are functions on this space which, in every chart, the functions are obviously Laurent polynomials. But since a union of charts, not every Laurent polynomial is a function on this space, so a subset of them is. And this subset has, well, of course, if you take just one torus, you have a basis of monomials. And this is a nice basis in the space of functions on one chart. But if you just take the union of charts, then you have still, well, in this particular case, so it's not any union. So it's such a union that still there are plenty of Laurent polynomials, which are, well, with plenty of holomorphic functions. And there is a basis of this function, which is the same size as OC star to the n. And this basis of functions on this space is, well, the basis of functions is enumerated by some discrete set, like z to the n. And there is another space which is called X tropical, which is also can be presented as a disjoint, as a union, not disjoint, of course, union of z to the n. Well, it's a little bit over notation to write as a union because, well, here all the different charts do not coincide, but here all the charts coincide. So this is just a union. It's a little bit trivial way, the union. But so you have charts. You have some manifold were glued by algebraic or even, well, rational maps, birational maps. Here you have charts glued by tropical birational maps, so the maps which are tropicalization of birational ones, and this is a, well, as a set is just z to the n. And there is a claim that the basis here, so basis of functions on here, basis of functions on A is, well, is equal to this space. So this is the cluster duality. It's a kind of Fourier transform. So usual, well, if you have the example number 0, you have the C star, and on that, of course, you have the space of functions which is z to the n, and n is integer, but you should think of this integer as a tropical integer. Why? Because this function is, of course, invariant. If you take z to the minus 1, you inverse z, and you take minus n. This is equal. But minus 1 tropical is minus, well, 1 over n tropical, so it's equal to 1 over n tropical. So this is a kind of, well, there is a generalization of this this phenomenon for more complicated situations. So this is just well, the what is cluster duality. So this is already mentioned several times, but under different names, perhaps. Second thing is just while not considering all cluster varieties, but also only cluster varieties corresponding to bipartite graphs, planar bipartite graphs. So cluster varieties from planar bipartite graphs. Well, planar, rather, maybe I should say that these are ribbon because they are just on the surface, not necessarily on plane, but the beginning of the plane. And well, these are actually its point of view also, which was mentioned in Orion's talk, that we are speaking about Metroids. So if you have a graph, bipartite graph, then you can associate a Metroid. I'm not 100% sure this is the same Metroid that in Orion's talk, but it seems to me that it's the same. So let's consider the simplest possible example. This is this graph. I will just explain on this example. So which Metroid it corresponds to? So I want to say that there are four points, which I enumerated 1, 2, 3, 4. So all white vertices correspond to points, and black vertices correspond to collinear points. So for example, here it means that we have 4 points, such that 1, 2, 3, 1, 2, 4, and 3, 2, 4 are collinear. Collinear. Pardon? Points where? Well, in projective space, in a projective space, minimal possible. So, of course, if you have 4 points, then they can be they can be collinear only on a line, so it's in one dimensions. If 1, 2, 3, 4. So if these are collinear, or 4 are collinear, of course. And well, this picture corresponds to configuration of 4 collinear points on the line, and we want how to parameterize the space. Also, this picture helps to parameterize the space. Namely, we have, for example, we have 4 points in projective 4 points in the projective space in P. Well, n which is not defined. Usually, n is equal to number of white vertices minus number of black vertices minus 1. So this is a number of black minus white minus 1. And how you parameterize this space? It's just you take the corresponding.
Maybe vice versa. White minus black.
Yeah. White minus black. Thank you. And how you choose coordinates? You just take the since this let's lift it in the vector space. So we have 1 tilde will be a vector corresponding to this point in the projective space. So it's a vector. So of course you have, I don't know, A times 1 plus B times 2 plus C times 3 is non-trivial, really equals to 0, and D times 3 plus F times DE, E times 2 plus F times 4 equals 0. It's just because they are collinear, so there is a relation between them. And you can put all these numbers, A, B, C, D, F, on this graph. So it will be A, B, C, D, E, F. And you should imagine these numbers as just one-dimensional homology, well, connection on this graph. So moving from this vertex to this vertex, you multiply by f. So it's one-dimensional discrete local system with connection. And the monodromy of this connection is to go around the quadrilateral, though you make a coordinates which is equal to x equals, in this particular case, it will be fb over ce, and with the minus. Every time you go from black to white, you multiply. If white to black, you divide, and you put, if the face is 2n plus 2 has 2, then, well, there is some sign, which is not very important. So this is the coordinates. And it's an easy exercise in geometry, well, first year, or high school geometry. So to verify that if you instead of this graph, you draw the graph which is just this one, 1, 2, 3, 4. Then instead of x here, you will get x inverse here. So you parameterize 4 tuples of points by one number, and then there is this transformation which sends this number to its inverse, and this is a transformation of the corresponding to the transformation of the graph. So this is well, corresponding between, well, here I just claim that every bipartite graph, well, more or less, because you should now impose some condition of minimality, which I also skip, but many, well, at least you can transform every graph to something which gives you a configuration space, and the configuration space is easy to parameterize. It's a cluster variety. Now well, the example which is more, well, for me it was actually the starting point of all this business many years ago. It was the case, then you have actually infinite graphs, but infinite kind of periodic. So suppose you have a Riemann surface, well, any Riemann surface which is triangulated. Or in order to take the simple example, you have a torus with one puncture, and you can cut this surface into triangles. So this is a same thing as so the triangulated surface, and then you, well, there is no, how do they? So it's just triangulated surface, and then you can construct a graph taking white vertices in here and black vertices in the middle of the triangles, and connect them like that. Well, of course, I assume that the left-hand side is glued to the right-hand side, etc. So this is a graph on the torus. But my construction works only with planar graphs. So in order to get planar graph out of graph of the torus, you can take a universal cover. And so what you get on the universal cover, you get triangulation of the upper half plane, etc. And the graphs, maybe I should have drawn by other color, sorry. It's just a universal cover of that. And you get infinitely many points. And so the graph will be, the bipartite graph will be like that. So it's some infinite bipartite graph, and this graph corresponds to configurations. So configurations of infinitely many points, collinear points. But of course, this is an infinite dimensional space. But I should remember that actually this picture came from this one. So therefore, I want all these monodromies to be invariant under the group. So there is a group pi1 of my surface. So this is not infinitely many points, but they are invariant, pi1 of sigma invariant, equivariant. Well. So it means that on this set of points, there is an action of pi1 of sigma, which is just here, in my example, just free group of two elements. But nevertheless, it's x on the projective line. And so I have a map. So therefore, we have a map from pi1 of my torus, or other surface, which is to the group to SL2R, or PSL, to C, well, or R, whatever. So therefore, since I have collection of points, but they are periodic, so I can say that instead of collection of points, I can just consider the induced map from representation of pi1 into PSL2C. So therefore, by considering this particular graph, I parameterize the space of focal systems on the torus. And this is the main construction, how to, the spaces which I'm mainly interested in today is just the space of focal systems on the Riemann surfaces. Now, this is for SL2. For SL3 is also possible to do the same picture for SL3. For that, let's consider example number 2. This was example number 1, and this example number 2 is a graph which looks like that. And I claim that, well, we have 1, 2, 3, 4, 5, 6. So we have 6 points, and 1, 2, 6 are collinear. But so I claim that this corresponds to just 6 points with three collinear so we can 2, 6, 4. 2, 4, 6, and then 1 is, sorry, maybe other way around. 1 is 1 is collinear of 2, 6. It's 1, 3, and 5. So it's configuration of points on a projective plane now. It's something two-dimensional, and it's clear that, well, it's also one-dimensional object. Well, you can compute the space of configuration is also one-dimensional. And the coordinates on that will be the monodromy around this hexagon. So this is well, the dimension of the space of configuration is equal to the homology of the original graph. Now, if you can generalize it equally well to any surface. So you have a surface which is triangulated. So you take on any triangle on this triangulation, you put this picture which I just have drawn, and this will give a, and etc. Well, if you draw this picture, so you have a picture on the surface, and you take a universal cover, and the universal cover. So here you can consider this picture is a collection of 3 flags in P2. So here you will construct also infinitely many flags in P2. And therefore, since they are invariant under the pi1, so it's homomorphic. Yeah, I obtain the homomorphism of pi1 of sigma into SL3.
And the round puncture go to...
And the monodromy round puncture is non-trivial.
But it's in Borel group? Or?
Yeah. No, not necessarily. Not important. It's just, well, I want to, it's a little delicate here, actually. What I get here, I get a monodromy, a map. So once you have a map, the question is how to restore points. The answer is the points are actually eigenvectors of the map around the point. So here there is actually, well, it's really plus choice of eigenvectors. Around the points. And the same thing here, you need to choose the invariant flag, and it can be done generically 6 possible ways. So this is not actually isomorphism, but the covering, because there is this choice of flags. So this is a well. Now it's really a part which is quite well known for a long time, and what I want to say now is that this construction is kind of abelianization. So we make something abelian out of something non-abelian. And why it is the case? Because, well, what I constructed essentially. So yeah, I constructed, well, for example, in by this construction, which gives birational, at least birational homeomorphism between the representation of pi1 of my surface sigma into SL to SL and, well, in this particular case, SL3, but in general it can be done for any n. It's just you take a triangle with more white points in it. So you have SLN to the first homology group of the graph, this coefficient in the multiplicative group. Which, well, this class of homology is given exactly by these numbers on edges. Because, well, the choice of the relations and choice of lifting of vectors change the chain, but doesn't change the homology class, so it's really correspondent to the homology class. Now, what I want to say that gamma is a graph, so I want to really find the surface. Well, it's a little bit more convenient to speak about surfaces, not about graphs, so something two-dimensional. So kind of surface, which is the same homology as the graph. And how to construct this surface? So sigma, by definition, sigma tilde is equal to the graph union with disks or semidisks. Disks or punctured disks.
Maybe you can say just you put ribbon structure on gamma, which is usual on black and opposite.
Opposite on white. Yeah. This is a different ways to do the same thing. Yeah. You just take all the edges. You take the Riemann structure, connecting for every edge. You replace Riemann structure by a half turn, half twist, and then you get something which is, you get another surface with another topology. Another way to view the same thing, you just take the surface and glue the disks along this of semi-disks, depending on where you on infinite plane or on a finite set. So you or semi-disks along zigzag paths. And those are exactly paths which Lorin explained. If you turn right at every white and left at every black. So for example, for my first example, you have imagined that you have a disk, you have four vertices. So you have zigzags which is this zigzag, this zigzag. So you glue two semi-disks to these two zigzags, and then two semi-disks to these two zigzags. Well, maybe it's not very intuitive to what I drew here, but the idea is that you get a double cover of the disk, ramified exactly these black points. So another way to look at that is that if you have a white three-valent vertex, then you cover, your zigzags go like that, and so you cover this side, and this side. So all three semi-disks glue into a smooth point. And if you have three-valent black vertex, so you glue here, you glue here, and you glue here, and you get double cover ramified at one point. So this is a surface which sigma tilde is a surface which is definitely not, well, first of all, it's the same topology as gamma. So homology is the same. H1 of gamma as sigma tilde is equal to H1 of gamma. And on the other hand, there is a map, is a covering. Pi, which is a map from sigma tilde to sigma, is an n-fold covering.
So each zigzag path should surround at least exactly one white vertex, like this. Yeah.
Yeah, right. This is a very particular. This is true exclusively for those pictures which are for SLN. Here, if every zigzag path, actually, you can verify that every zigzag path is actually contractible. This is not the case if you draw just arbitrary graph, of course. And this is, for example, for integrable systems, there are also this description, and there the zigzag paths are not contractible. This is very important. But here they are. And so you have really the covering of the surface. So, okay. Now the question is the following: what is the what I want? Well, main question was which I will address now. So this is what is the tropical limit of this picture. So why I need tropical limit? Because tropical points correspond to functions on this very space. So it's some discrete picture, which is discrete set, which I want to describe in some way, which is not just saying that this is a tropical point of some another variety. So the question, what are tropical points? Of this representation variety, pi1 to SLN. And the answer, well, first answer, well, it's just tropical points, which takes H1 of sigma tilde with value of C star, and makes it out of it H1 of sigma with value in C, because it is and Z, sorry. Just tropicalization of C star is Z. So H1, everything is linear, so this is very easy. So you have, as a tropical point, you have some integral classes of this variety. And it's really, if you do it in coordinates, it's really, well, tropical coordinates on this space are just, well, the same, essentially, well, if you do tropicalization, just replace complex numbers by the integers, and you ensure that well, integers is a semi-field, so you can add and you can add, multiply, subtract in tropical semi-field. So you can replace really C star by Z. Now, how you can interpret this? But now the question is how you can interpret this geometrically. So they remark that in dimension then n equals to 3, then is equals to 2, sorry. For there is an answer that H1 of sigma tilde and Z is the same thing as what's called measured laminations. And this is our just collection of curves. So you have, well, measured integer. So it's just a collection of curves without intersection. Well, if you have points, marked points, you have some additional words about how you treat these points. So every point you spiral either in one direction or another or whatever. But these are just for closed surfaces, for example, it's just collection finitely many closed curves. And if you have finitely many closed curves, you can construct very easily a function on your space, moduli space, because you take trace of monodromy around this every curve and just multiply them. So there is a way to describe functions on your cluster variety using this lamination. So the question is, what are laminations in this higher case? And this is the
surface without function, it's not cluster variety, but still.
Yeah.
It's still get kind of abilization, yeah.
You still get an abilization, I think. Yeah, right. What is also important, maybe I should mention that what is important to just interpret it as a sigma tilde, so it's as a surface, because you get a Poisson structure out of that. H1 of sigma tilde has a Poisson structure because it has intersection index on it.
First homology, maybe lower one.
For Poisson structure, you have
you get pairing on first homology if it's open surface.
Well, it's A space and X space, just cohomology. If X space is cohomology because it's not always defined, and this is because it's Poisson structure and not symplectic, well, something. Yeah. So there is. Now the answer, which I suggested answer. Answers to the question, what is the geometric meaning of that? So there will be some colored graphs on the surface. So colored graphs on the surface, instead of this collection of curves, which are not colored, now we will colored graphs on the surface. And how to construct a colored graph out of the element of H1 of sigma tilde with values in Z. So, first of all, let's take H, which is H1, just first homology group of sigma tilde with values in Z. So you can imagine that as a one form. So alpha will be in one form, representing generic one form, H. And then you can define a map which is sigma tilde to the S1 cross sigma. So it's two-dimensional manifold to three-dimensional. How you define the map is just you take the point Z, and it maps to the point integral of alpha up to Z, comma pi of Z. Pi is just a projection of sigma. So you have a map, and of course you consider S1. Well, this integral is defined up to an integer, because it's integer homology class. So you have, if you consider that modulo integers, you get an element of the circle. So you have this map, and now I claim that this map is what are the singularities? So 3 to 2, you have plenty of intersection points of this map. So you have in three-dimensional space, you have two-dimensional surface which self-intersect, and if you project it on the base, so you have an edge, you have edges. Now the question, if alpha is of generic, the question is what are possible singularities of this, well, singularity of singularities. So you take singularity, you take that. So what you get, I claim that generically there are three types of singularities. So one singularity is just trivalent vertex. Another singularity is four-valent vertex. Then just two lines projecting the same. And there are also, if you have triple intersection, it corresponds to six-valent vertex. These are ramification points. Ramification points and only ramification points give three-valent vertices. These are two-valent vertices, these are four-valent vertices. These are six-valent vertices. Moreover,
and this six-valent vertex is not a combination of these two three-valent.
No. These are ramification points, and these are just triple intersections. So we have three planes which intersect, and they intersect until you get three. Moreover, you imagine that you can enumerate the edges, color the edges. Edges are colored by generators of the group W n hat, which is affine Weyl group. Why it's the case? Because so you have a surface sigma. Let's take a path on the surface. So now let's take over each path there is a circle, and so you have a circle. So over a path you have a cylinder, and if you intersect the cylinder with the sigma tilde, it will give you something like that. So some diagram of this type. So these are just sigma tilde, intersection of the circle with the image of sigma tilde. So if you move along the path, these points move. And each time two paths, there is a singularity which is correspond to the point where, my graph intersects the path exactly where these lines intersect. But on the other hand, these diagrams is just, those diagrams, this set of such diagrams is nothing but the group W hat. So the set of diagrams with respect to usual juxtaposition of the diagram. So this is the W n hat by definition, and this is the group generated by the generator Si, such that Si, Si plus 1, Si equals Si plus 1, Si plus 1, Si plus 1, where I is just Z over NZ. So it's cyclic generators, and this is W n hat. So you have the graph, which is now the edges are covered by SIs. And the rule is the following, that if you have triple points, then you have SI, SI, SI. If you have you have SI as J, SI minus J is greater than 1. And sextuple is, I write is I, J, I, J, I, J, I minus J is equal to 1. So this is actually these vertices are relation in my group. So this is nothing but the relation of the group. And so, in particular, this graph, for example, can be generalized to any types of the group. Though I have no interpretation of these graphs in terms of Lagrangian submanifolds. But here is just a very explicit interpretation. And now the last moment, well, I cannot say much more, but just the last statement that the same graphs appear in different contexts. Well, in one context is the work of Alias and Williamson. So first it's Alias Williamson. They speak about they construct, using these graphs, they construct some intertwiners between products of Zergel bimodals. And this is just the same thing. So this is something which maybe I should not comment at all. Second thing is just the same graphs appear if you make computation in, so more simple computations in the Hecke algebra of, well, HQ hat because it's affine of W. So if you multiply two words, so HQ of W is the same as a Weyl group, except that you have additional relation that SI to the squared is equal to Q minus I 1 SI plus Q. So if you have a word and you in these letters SI, well, SI1, SI2, etc. So what you can, then you apply relations, then you can either, well, if you apply this relation, you have two terms. One term corresponds to this trivalent vertex because it reduces the number of if you have SI, you have SI, you can also contract them and give this coefficient Q, this is coefficient Q minus 1, etc. So in computation in Hecke algebra, you also get these graphs. And the third context is the third context is the following. So very briefly. So let's consider the representation of the pi 1 of sigma into SLN hat. So it's a affine group. And then we can do the following. You can, and let's take consider this graph G is compatible, well, the graph which I described right away is compatible with, well, I don't know, R in this space with R if there exists over every face of gamma of G, there exists a covariant constant flag, which of course is an affine flag, such that every time you cross a border, so you have this flag F1, this flag F2, and here we have SI. So you want this, the pair of flags F1, F2 be, well, at the distance SI. So this means the pairs of flags up to the group action are enumerated by the Weyl group. So this is just the distance between flags. So there's a kind of compatibility condition between graph and the flag. And, well, it's not definitely not a theorem, but some examples, however, computed, that it gives a kind of cell decomposition of the space. So it means that, well, cells in the sense that cells are not cells, but product of C stars and Cs. So it's not topologically trivial, but what it gives, it gives a kind of approach of finite dimensional filtration of this huge space, which is I've always dreamed to figure out what the meaning of this space, and here is kind of approach to this question. Okay, thank you very much. Sorry for speaking so long.
Questions?
Yes, question. Yeah. In your construction, you have this covering sigma tilde, yeah?
Yeah.
And also map from the covering to S1, yeah?
Yeah.
Yeah. But these things have kind of geometrically continuous parameters, yeah? Because you have different sheets and how
Sorry, no, of course continuous, but no, if you move your surface, so for example, you change this form to an exact one, so those are, well, yeah, those graphs move, of course. But well, something which I didn't mention, what happens to this graph? So of course there are some equivalents.
Okay, so there is some kind of invariance.
Some kind of invariant. So, for example, if you have this picture, then this is the same. It's a trivial thing. The same thing as this one. So we can move them, and there is all relations are trivial except one, which is, well, I could draw, but it's a little bit long picture, and we did it. We found it from this Lagrangian point of view. One thing I forgot. Should say it's a joint work with my students Alexander Thomas and Waldo Tatishev. Yeah, and we did it for Lagrangian case, and in Alias Williamson, they have the same relation. Well, first we computed that for our case and found the same in their paper, which has nothing to do with Lagrangian submanifold.
Yeah, so in relation to the affine Weyl group that appears, like it's not just the type A one, right? Like you also get the other types which corresponds to like the 4-valent graphs and 6-valent graphs, like type G and type B.
Yeah, well, yes, and since that this can be easily generalized. I have no interpretation in terms of spectral curve. Spectral curve, this Lagrangian submanifold. So it's not necessary for any homomorphic spectral curve. There is a you can try. It's very rare that homomorphic spectral curve has integer class. That's the problem why you really need to consider smooth ones. But roughly, this submanifold is spectral curve. Yeah, and well, this construction can be generalized for any other type, of course.
Yeah, because the part that I'm confused is that with at least the group that you've written up there is like a type A Weyl group, right?
Yeah.
Type A affine Weyl group, and even within type A affine Weyl group, you still get graphs which are 4 valence and.
Yeah. These are just relations. For AN, there are two types of relations. Well, there is a relations of commutation. It corresponds to commuting of different generators. This coincides to braid relation.
Yes. I got confused. That's correct.
And for B, you need to have an 8-valent vertex, and for G, how many?
Yeah.
But for B, you can consider folding.
Maybe one can consider. Yeah, this is a remaining question, which I would like very much to figure out what is that.